Hey everybody, how's it going? My name is Jack, and today I wanted to make a video covering some of the details of a project I completed last year, share an opportunity which came about after I completed the project, and also do a demo for an app that I made. So as some of you may know, in October last year, I completed this project and published this post where I fine-tuned a Whisper medium English model on air traffic control data that I found online. And I ended up getting a 15.08% word error rate, which is a 84% relative improvement over the base model. So this blog post essentially just covers an introduction to the project. It covers the problem or the motivation for the project, which I can quickly cover now. So it's been found that the vast majority of aviation accidents occur at some level due to some miscommunication or just communication errors between air traffic control and pilots. Whether that's misunderstanding something, whether that's misremembering something, or just forgetting to ask at all. It's just been found that these errors really contribute to a lot of the accidents that we see. So I sort of proposed a solution, or thought of a good solution here, which is in recent years we've seen a huge improvement in AI models that have come into the market, like open source models as well. So in the automatic speech recognition sector, Whisper came to light a few years ago from OpenAI. Now, Whisper models are tremendously accurate in so many different contexts, but one context which they fail in quite dramatically is ATC communication, most likely just to a lack of exposure during training for the base models. So what you can do though is you can take a Whisper model and then you can fine tune it on a specific modality of audio. In this case, I chose air traffic control audio. So that's communication between controllers and pilots. And this will ideally, in the best case scenario, expose the model to more varied examples and just more examples in general of this audio modality, which will make it better attuned to doing better and more accurate transcribing of this audio. So that was the solution, and I didn't have the budget for a lot of the big commercial ATC datasets which exist. So I had to use what was available online already. So on Hugging Face, I found that there were two datasets publicly available. One of them is the test set for the ATCO2 dataset, and the other one is a dataset which comes from the University of West Bohemia, Department of Cybernetics, and then so these two datasets were already online, but they were online separately. So what I essentially did to create the custom dataset was I just downloaded these two datasets, I combined them together and standardized the column. So it's just an ID, an audio, and a text. Standardized the text such that it's just all lowercase and it doesn't have any symbols or anything inside of it. So I cleaned up the text. And I also got rid of any erroneous samples from the set. So some of the ground truths were actually incorrect to the corresponding audio just due to human error, which is actually really bad in a context like this because you really don't want to expose the model to any incorrect training cases. Otherwise, it's just going to get confused and the overall results that you're going to get are worse. Anyway, this blog post covers a bit more of the fine-tuning process, the evaluation metrics that I chose, the actual process itself, some of the limitations. Over here are some of the examples where the ground truth was incorrect for the audio. So that's over here. And then I also created an ATC transcription assistant, which is on Hugging Face, where essentially you can pass through an audio file and it'll run it through the model, and then we can see the result. Now, the demo that I have to show today sort of is a bit of an extension of this, an updated version of this, but it's not yet on Hugging Face, so I'll make sure to do that. Okay, so as a result of this project coming out in October, about a month later, so this came out October 9 and November 17, Eric Button, who is the sort of founder, CEO of the Enhanced Radar company, reached out to me and essentially said that his company is trying to do what I did in a commercial setting, more data, do their manual labeling of data, and essentially trying to really improve safety in aviation, especially at airports. So a lot of what they were focusing on was more trying to create software on the ground at airports that controllers could use that would do threat detection and prevention, and also show logs of sort of what's being said and compare that to what planes are really doing, to see if we can flag cases where errors might happen, runway incursions may occur, and ultimately lead to these sort of aviation incidences. So part of doing the work for them, they bought a data set and gave it to me to use. It was just one data set that was US data. It was like a US data set. I think it covered like three airports, one of which was Boston Airport. I just forget the other two off the top of my head. And they gave me this and they said, we want you to use this data, train a larger model on this data and see the sort of results that you can get. So I decided to go for the newest model that was released by OpenAI at that time. So, and still currently to this day, which is Whisper's large V3 turbo model. There was some debate that I had whether I wanted to use the standard Whisper large V3 model as opposed to the turbo model. And I read some things where the accuracy may be a little better with the regular large model, but I decided to go with the turbo model just to hopefully make inference as quick as possible, because ideally this model has the same performance, but it's substantially quicker. Now, so the app that I'm also about to show you, it uses the model, but this isn't covered under the confidentiality. But this model and the weights for it, I unfortunately can't post online. But I did get this model down to 5.8% word error rate, which I was pretty pleased about given the data that I had access to. And there's no doubt in my mind that this can't be improved even further if we use even more commercial data sets, combine them into one big data set, and even create our manual data labeling system and get these also running in the model. But that's for companies to do. But just as like an ML engineer, it would be ideally what I'd love to do is get this data set and a few other of the large commercial ones that are available, combine them, and then see what I can get there. Anyway, so the app, the way that it works is it's essentially connected to Live ATC, which, as some of you may know, is an application where, it's a website that you can go on to listen to live air traffic communications between pilots and controllers at various airports. So I'll quickly get into the demonstration. So it's just a flat application. But if I run this, Python app.py, what's going to happen is it's going to load the fine-tuned model, and it's also going to load this open source speaker attribution model into memory, and then open the application here. Perfect. So this is the app, and I'll do a demo, but I just really want to quickly show this model. So essentially, this does speaker attribution. It's attributing pilots or ATC to a communication, and it's doing it on the text level. So you pass through some text, some utterance, and then it's going to pass it through the model, and then it's going to output sort of classification of this is either pilot or ATC. Usually this is done at the acoustic level, they say, but they're proposing to do it at the text level. I'm not entirely sure how accurate this model is, so I wouldn't put all my eggs in the basket for it. This isn't really a fantastic like speaker diazoration model, which is doing like proper speaker attribution of like a call sign or something like that. But it's sort of just the best that I could get at a moment's notice. So that's what I'm using at the moment. But the basic way the app works is, we're gonna make it full screen here. You type in an airport code. So I like to do Boston, the Boston Logan Airport, I believe it's called, International Airport in America. So the ICAO for that is just KBOS. Then you hit enter, and then it'll do a scrape of the airport and for the available frequencies, available on live ATC. We've also got some logs here. So we can see it just fetches the frequencies, fetches the streams for it, and then loads the streams here. So then what we can do is we can select any one of these frequencies, and it'll begin doing live transcription of it. So I'll just click on Boston Tower, and we can see what pops up. So essentially what's now happening here, we've already got some coming through. So I'll play some of these in a moment, but I just want to explain a little bit about sort of like what's happening here. So we have the live stream of audio, and FFmpeg has this real-time streaming feature, which is really cool, where you can pass through like the live stream link, which is associated with a live stream on live ATC. And we can run a voice activation detection, so a VAD system, directly on the live stream. Now, I tuned that up, changed some of the hyperparameters around with, getting rid of like segments which were too short, and making sure that the threshold, like sensitivity level, was adequate, was like not too sensitive, but also like not too like hard to listen to, because like we don't want it to. We don't want some actual samples to like not show up here. And then it essentially segments them into WAV files, resamples them to make sure they're 16,000 kilohertz. And then it will pass each one into a queue. And then this queue gets sent to the Whisper model for inference. And then that spits out the actual text that we get here. And then you can see where it's doing the ATC and the pilot attribution, which may be correct and it may not be. So again, I wouldn't believe these all the way. This is happening with that model, that open source speaker attribution model that I covered earlier. And then I have a play button. So associated with each one is going to be the audio itself that we can listen to at any time. And then also a timestamp of when this audio was, like when this transmission had finished. And yeah, so then we can also see sort of the time. But I'll play a few now. So if I'd run this, we should see that one. It does take a while when they're playing.
Blue 8363, kind of fast on the fire. You're gonna
have a good night, Jeff. Blue 8363.
Heavy, runway 33 left, clear for takeoff.
Runway 33 left, 34 takeoff, search 5 for Albion.
At the moment, I just don't have my headphones with me.
Skipper 541, crossway turbulence, departing heavy, Airbus 350, time to land on the crossing runway, runway 33 left, line of runway.
Well, but it's not always doing fantastic. Sometimes I like to think that I attribute this to the fact that this model, because it's only seen like one data set, it could be that in aggregate it's been trained on a data set, and then this 5.8% word error rate is we get to that by running it on the evaluation of the data set. Now, the way that these, the data set is split is like we have this whole thing, and then we just take 80% of it and we put that into the training, and then we do a 80, and then the 20% goes to testing, right? So if you think about it, aviation communication is this like really broad general thing. We're going to have pilots coming from all around the world, especially to a really popular airport like Boston International Airport. These pilots are going to have different levels of English proficiency, accent differences, and also just differences in the quality of the microphone. So what we may actually find is that the model does substantially better on the test or evaluation cases for that data set. Which doesn't mean, because but it's a bit of like a second order thing, right? Because like when training machine learning models of any type, generally you don't really account for that latent bleeding in from one data set to another, That's why we separate these out into training data and test data to make sure that the model has never been exposed to the samples that it's getting tested on. But it could be that it's a bit overfit for the data set itself, and that it doesn't generalize amazingly to, excuse me, many different airports, different people and stuff. That's why I'm choosing Boston Airport, because I think we have the best chance of
American 1597, we're 8.5 out, that was 27.
You can see for a lot of these, it's actually doing a pretty damn good job.
1597, good evening. Calling Boeing 757 on a 5-mile final. Have to hold them across the runway, runway 27, clear to land.
There we go. So, and then if you wanted to run a different airport or a different frequency, you could just hit back. You can select whatever frequency that you want here, back again, and then we can type in a new ICAO code. It'll do a new scrape. So in this case, it's Sydney Airport. And then we can like pick some of the frequencies there. So I can do the ATC or Sydney Tower, for example, and we can start to get that running. We can see the logs here running. Anyway, that's all that I have today. I just wanted to cover the demo for the app. I'm going to make sure that that is on Hugging Face as well, on the Hugging Face space, to make sure that other people can also use this if they want and just pass through whatever airport code they want. Other than that, thank you for taking the time to watch this today. I hope this was at all helpful, and I'll see you guys next time.